So today we are very happy to have Anthony Munson from University of Maryland, College Park. Am I pronouncing your name correctly?
Yes, Anthony Munson.
Thank you so much for accepting to give a talk. And please, he's going to talk about quantum uncomplexity.
Great. Well, thank you so much for inviting me. I'm very happy to speak about this today. I'll try to the best of my ability to speak a bit to the high energy implications of this topic, although as you'll see, it's of even more general applicability than that. So today I'll be speaking about the resource theory of quantum uncomplexity. My title accordingly is Quantum Uncomplexity, a Resource for Quantum Computation. So before we talk about uncomplexity, let's just get straight what quantum complexity is. So quantum complexity quantifies the difficulty of preparing a given quantum state from a simple tensor product state. The natural example that we will use throughout the talk is just the n-qubit all-zero state, and that typifies a state with low complexity. Now, there are different ways that we can give a mathematical definition to quantum complexity, but the best starting point is the exact unitary complexity on n qubits. So this is the notion of complexity that you would first think of. If I start off with the state psi, I want to implement some number, or rather, my bad. If I want to create a state psi and I begin with the all-zero state, then I want to perform a certain number of 2-qubit gates to form a circuit that will implement a unitary U. That unitary U applied to the all-zero state will create this state psi. So basically, I start off with a lot of zeros, and I apply some circuit. It has a certain number of gates, and that'll yield psi. Now, there are different ways that you can do this, and the exact unitary complexity of the state will just be the minimum number of 2-qubit gates that achieves this task. So just for notation's sake, we denote the quantum complexity of the state psi by C of psi. Now I've stated what quantum complexity is, but we want to know why it's even important that we discuss this topic in the first place. So quantum complexity has become increasingly relevant to a number of fields in physics. The first and maybe most obvious is just that of quantum information. So it's been shown that complexity can quantify the difficulty of discriminating states and of preparing superpositions. Moreover, in condensed matter physics, it's been shown that complexities that scale linearly with system size can distinguish topological phases. And lastly, in high energy theory, there is a conjecture in ADS-CFT. So if I have the state of a wormhole connecting two black holes in the bulk, I can look at its dual field theoretic state. And the complexity of that field theoretic state is conjectured to be proportional to the wormhole's length. So this is coming from work that I'll reference later by Brown and Susskind, in which the notion of uncomplexity was first really investigated in detail.
Question?
Yes.
Are you gonna say more about this, the first one, quantifying the difficulty of discriminating states?
No, I can give you, that's not so relevant to the
Okay, I don't want to derail the talk. If I was just asking.
Yes, but I should say, and perhaps I should have said this at the beginning, I have a version of this that I recently updated with references, and I could not find it shortly before this talk. So I have these references for the quantum information. There are a couple of papers that I can send over the chat shortly after the talk for the reference. Yes. Okay, so now we've discussed what quantum complexity is, and we want to know what is uncomplexity. So before we can even, so really uncomplexity is just the lack of quantum complexity. Now you might ask, okay, how can I quantify the lack of complexity if I don't have a maximal complexity? And what we have to establish first, this is by a counting argument. Again, I can give you the reference later. By a simple counting argument, we actually see that every n-qubit state has a maximal complexity. So the maximal complexity goes like e to the n, where n is the number of qubits. And so once we have a maximal complexity, we can actually talk about a lack of complexity. So the uncomplexity of the state rho is the difference between the state's complexity and its maximal complexity. So to give just a bit of intuition, in the case where we have a state with very low complexity, as I say the all zero state, we define that as a state with zero complexity, then the difference between the maximal complexity and the state's complexity would simply be the maximal complexity. So in that sense, a state of the all zero state would have maximal uncomplexity because it is relatively low in complexity in comparison to other states. Okay, so we've defined uncomplexity, and now we want to get to motivating the crux of the matter, uncomplexity as a resource. So there are a couple of motivations here. So the first is complexity growth in systems with random dynamics. So it turns out that in systems with random dynamics, the complexity of the system increases linearly 4 times exponential in the system size. So that's far longer than most other observables thermalize. And as a result, we can think of complexity saturation as a late stage of quantum thermalization. And in that sense, complexity is a good parameter to track the evolution of such systems across time. And for experimenters who want to have systems that have not yet undergone random dynamics and thus are relatively controllable, it's useful to think of uncomplexity as characterizing the system being in a relatively well-known state. So a useful analogy here for bringing it to quantum computation is that useful states in quantum computation are like blank qubits. So in the same way that I often want to begin writing an essay or a paper with a pencil on a blank sheet of paper, often it's useful, let's say in the case of Ancillus for quantum computation, to have states that are relatively uncomplex, so that way I can easily manipulate them for whatever purposes I have. And then lastly, going back to the high energy topic that I mentioned previously, there's a conjecture that uncomplexity can be formally understood as a resource in quantum computation. So this was a conjecture given by an influential paper by Brown and Susskind, and is what has sparked a lot of the interest in complexity and specifically uncomplexity going forward. So in particular, it provided the conjecture that in this paper, the resource theory of quantum uncomplexity, we confirmed. So this paper is on the archive. We put it up in late October of last year, and it confirms the conjecture that we can indeed define a resource theory of quantum uncomplexity, and it establishes not only the definition for that theory, but also defines operational tasks and quantifies the efficiencies with which we can perform those operational tasks in the resource theory. Okay, so now let us get to the overview of the talk. First, we're going to define the resource theory of uncomplexity, after which we'll move on to the operational task. There will be two of those, and we'll establish what those tasks are, and afterwards we'll want to quantify the efficiencies with which we can perform those tasks. As an interlude, we will define the complexity entropy, which is used in the two theorems we have, which quantify the optimal task efficiencies. Okay, so now let's move on to the first topic of the talk. This is the resource theory of uncomplexity. So before we talk about the resource theory of uncomplexity, let's just establish what is a resource theory. So a resource theory is a rather straightforward but very useful and powerful concept. In a resource theory, an agent can perform a chosen operation that satisfies some simple rules. Now, this notion of simplicity is just in context of whatever rules are provided. The intuition here, however, is that states that are difficult to prepare are scarce resources and can facilitate operational tasks. So you can just think of any resources you might want to achieve some task in everyday life. Maybe the easiest you can imagine is just having money in a capitalist economy. And in the case of, I'll give a few examples in the next slide for examples within physics. Lastly, we should just be clear, a theory is defined, a resource theory is defined by its allowed operations on a set of states. So once I tell you the set of states, and I tell you what your allowed or free operations are within the theory, then I've told you what you're allowed to do in order to manipulate quantities, substances, in order to extract or manipulate the resource that you're interested in. Let's look at.
So, as you said, usually resource theory is defined using the set of allowed operations that lead to a definition of, you figure out what the free states are based on the set of allowed operations.
Yes.
But could you go the other way around? Could you start by saying, I'm going to declare state 1, 2, 3 as these are free states, then the set of allowed operations are going to be things that will not, can you go the other way around by defining it and using the free states?
Yeah, so this is a very interesting question, and I'm going to, whenever I talk about the resource theory of uncomplexity, we'll get to this distinction. So resource theories always have free operations, but they don't always have free states. Typically, they have both, or at least typically among the resource theories a lot of researchers look at, but it's not without precedent to have a resource theory without free states. And indeed, as I'll discuss later, in the resource theory of uncomplexity, we can't have free states, or else we would trivialize the theory. So the idea here is that we have some specified states, so that we can even contextualize the allowed operations. But I don't think in general that I think in general the resource theory is defined by the allowed operations. Free states can be determined as a result of that. Basically, free states would just be states that would not give you any more of the resource whenever you apply the allowed operations. But I don't believe that you can go the other way around where you start off with the free states. I think even having a free state kind of implicitly appeals to what operations you would be allowed to apply. Does that answer your question?
Okay, thank you, yeah.
Okay, so now we talked about what a resource theory is in abstract. Let us make things a little bit more concrete by looking at a couple of examples of resource theories. So the perhaps canonical example is the resource theory of entanglement. So the two resource theories I'll discuss on this slide do indeed have free states. So in this case, the free states are just separable states, namely those which feature no entanglement. And then the free operations are what are called LOCC operations. So ones in which you can perform local quantum operations. So I'm able to do quantum things, but it has to occur in my local laboratory. And I'm also allowed to perform communication, but it has to be classical. So I'm not able to apply general quantum channels in which I can generate or leverage or generate entanglement as a result of my operations. Okay. So moving from quantum information to thermodynamics, there is a resource theory of athermality. So in this resource theory, our states are going to just be systems defined as pairs of density matrices of states and time-independent Hamiltonians that determine the evolutions of those states. So in this case, our free states will be states in thermal equilibrium, otherwise known as Gibbs states. And our free operations will be those processes that conserve total energy under system bath heat exchanges. So the intuition here is that we can use a lack of thermal equilibrium that a state possesses, some distance from thermal equilibrium in order to perform thermodynamic tasks such as work extraction. And so this resource theory is interesting because the lack of thermality you can think of as parallel, analogous to a lack of complexity. Not in any rigorous sense, but perhaps it gives you some intuition here. Okay, so now let's actually discuss the resource theory of uncomplexity. As I said before, in order to define a resource theory, we're really just trying to define the allowed operations within the resource theory. We have a primitive notion prior to that we need to discuss. That is the notion of a fuzzy gate. So the fuzzy gate basically is a gate that suffers from some noise that we model in the following way. So if I have some desired gate U, then I will implement some gate U tilde with respect to some probability distribution that will vanish outside of an epsilon ball of that desired gate. Now, epsilon is some parameter which is greater than or equal to 0. In the case that epsilon is greater than 0, we assume that there is some open set containing the desired gate U that is supported by the probability distribution. So you can kind of think of, this is fuzziness around the desired gate U. There's some probability going in all directions of that gate U that we get some other gate U tilde. And moreover, the assumption is that we won't have any probability of getting a gate outside of some epsilon range of the desired gate U. So that's what the parameter epsilon quantifies. We don't have any other restrictions on the probability distribution here. Now, in order to quantify the epsilon ball more precisely, we need to state that the distance between gates in the set SU4, in this case, is given by the operator norm. So we that epsilon parameter just tells us that our fuzzy gate U tilde, it will be some distance less than or equal to epsilon from the desired gate U in terms of the epsilon norm, or my bad, the operator norm.
Sorry. So this fuzzy gate applies the quantum channel to the state, is that?
No, so, well, I shouldn't say no immediately, because perhaps you could render this definition in terms of a quantum channel. Nevertheless, the idea here is just that we have going to this physical interpretation, I mentioned in the second bullet point that we have this model of noise around a desired gate U. So an agent wants to implement some unitary U, but there will be some amount of physical noise as in any realistic situation. And here we're just giving a particular model of this noise, namely that there is some that the agent will actually implement some gate U tilde, which is within some range, some epsilon ball of the desired gate, and that the probability distribution, at least initially going from U, can go in all directions. Does that answer your question?
It is a quantum channel, but it's all right, yeah.
I'd be interested to understand in what way it is a quantum channel. Yeah, perhaps.
Sorry. So I have a question. Is
yes.
This tilde still unitary or is approximate unitary?
The gate U tilde is a unitary.
Okay.
Yeah. Okay. So that gives us our primitive concept, which is a fuzzy gate. The allowed operations are fuzzy operations, which can simply now be defined as compositions of fuzzy gates. And going back to the discussion we had about the previous slide, there are no free states within this theory. So let me give you the quick argument as to why this is the case. So the idea is that if I have an n plus m qubit state, that the maximally complex n plus m qubit state has complexity which goes like e to the n plus m. So this is coming from the counting argument that I mentioned earlier. But if I were to start off with a maximally complex n qubit state and a maximally complex m qubit state, and then I were to tensor the two together, I would get a new n plus m qubit state that has complexity, which is on the order of e to the n plus e to the m, which in general is less than the former complexity. So in that sense, if I were to allow tensoring on within my theory, then I would be able to create states with less than maximal complexity. And since that is true, I would be able to create uncomplexity from scratch. So as I said before, we start off with allowed operations. If there are a set of designated states that with the allowed operations do not create the resource that we want from scratch, then those can be our free states. In this case, it's not possible. So because tensoring on creates uncomplexity, this theory has no free states.
Sorry, question. It seems like this is an artifact of the thing that you're insisting on having pure states. So after one application of a fuzzy operation, you have density matrix, right?
Yes.
So to demand indeed, so it's like a quantum channel, and the invariant states of the quantum channel would be your free states. But there are no pure states that are invariant under this quantum channel because you're injecting noise. So indeed, if there was if you take a state which is identity, the identity operator, under any fuzzy set of operations, that will just remain the same.
So it turns out that in this argument is given in a couple of cases or papers. The one is the Brown and Susskind paper I mentioned before, and then there's also some lectured by Susskind. Even if you, in the one clean qubit model of computation, even if you tensor on I should say just generally, even if you tensor on a maximally mixed state, you will still create uncomplexity. It's still possible. So that's not as obvious, and I didn't put it into the slides immediately. I can give you the reference after. But even with the maximally mixed state, you still have this issue. So it's still true that there don't exist free states within the theory, and perhaps we can follow up later. Okay, are there any other questions?
I have a question. Ideally, if you can prepare the maximally complex qubit state, is that the free state? Because uncomplexity is going to be 0.
So you said if you compare the maximally mixed state?
Yeah, if you compare with the maximally, maximally complex qubit state to maximally complex qubit state, uncomplexity is 0 by definition, right?
The maximally complex state?
Yeah.
Yeah, so the maximally complex state will have yes, low on complexity. Sorry, I'm not entirely clear on the question. Maybe
sorry. So I think you
you
mentioned the definition of maximal complexity before, right? Like e to the n. So let's say you have n qubit state. I think the one you have like maximally complex on the slide, you have maximally complex n plus m qubit state has complexity e to the n plus m, right?
yes.
So if you have maximally complex qubit state, then its complexity is maximum, right? And if you compare two maximally complex qubit state, uncomplexity should be 0, right?
Yes, I see your argument. I think.
Yeah. So my question is, if you can have, like, ideally,
yes,
it's possible, but if you can prepare maximally complex qubit state, then that should be free state, right? In this story.
Okay. So yes. Okay, I understand what you're saying now. So here the free state would. So this argument explains why a maximally uncomplex state can't be a free state. Because if I were able to prepare a maximally complex state and I were able to tensor it onto another, I would actually create uncomplexity in the new joint state after I tensored it on.
Yeah. Okay.
Does that make sense?
Okay. Yeah. Oh, okay.
Yeah, maybe the subtlety comes from the fact that you once you tensor it on, it has this relative uncomplexity to the to the state or the maximally complex state that you would have just with starting off with n plus m qubits.
Yeah. Okay.
Sorry, can I ask? Can you say again? I think you said this. What is the definition of uncomplexity? So I have a state. I know what this complexity is. How do I define uncomplexity?
Yes. So it's a difference from the maximally the maximal.
Like, let's say I have n qubits. What exactly is the number I'm subtracting this from? Is it e to the power of n? What's the coefficient of it?
I'm not sure in this case. The counting argument doesn't. I would have to look at the counting argument again. I'm not sure that it's a step. Well, the issue here is that the model. So far, I've just spoken about 2 qubit gates, but you could consider different models of 3, 4, 5 qubit gates. And if you do that, then you won't determine an exact coefficient if you allow the variation. So I think the argument here was just given for the general k qubit case. I do think it for the sake of doing concrete computations, that's a worthwhile question, and perhaps someone has already answered it.
Thank you.
Sorry, can I ask one question as well?
Mm-hmm. Yes.
If you consider a system of n plus m qubits, is the maximally complex state unique, or is there a set of states that are maximally complex with complexity of order?
Yes, that's a good question. From my understanding, I don't have an argument on the spot, so you should be hesitant of my answer. But I don't think that there is here. Complexity is just defined as the number of gates that you need to, well, at least in that instantiation, exact unitary complexity would be the minimum number of gates you would need to achieve that state. So I don't believe that it seems highly unlikely. I don't think it's the case that there is a unique maximally complex state. And in fact, you could, yeah, I have a very strong intuition that that's not the case, simply because you could imagine, so to speak, going in different directions and in the space of unitaries. And you could go just as far in one direction as in another. So I think.
I guess if you have 2 qubits, you can apply any unitary and get different states.
Yeah. So then the set of all maximally complex qubit states have 0 uncomplexity.
Yes.
Will they not set of free states?
Sorry, what was that last question?
Wouldn't that set form the set of free states? Because all of them have 0 uncomplexity.
Yes, I think that this it was addressed by the earlier question. The issue here is that you have to, in order for it to be free, you have to be able to tensor it on and for it to provide no uncomplexity. So once you account for the fact that tensoring it on actually contributes complexity, right? Because you could say, okay, I have some.
For tensoring on, you are considering maximally complex states on a subsystem, right? Like if you have n plus m qubits, you are considering maximally complex states on n qubits and on m qubits and then tensoring them on. But can't you consider maximally complex states on the entire system? And then there is not tensoring on coming.
Yes, yeah. So that's where the argument comes from, is that I could consider it without the tensoring on, and I get a different complexity than I would if I were to tensor them on. So by tensoring them on, I can make a comparison between those complexities, and I see that I start off with less than maximal complexity if I tensor them on. So in that state, that way I could create uncomplexity by this tensoring on process.
No, I think the thing that confuses us is like if you have a quantum computer with, let's say, 1,000 qubits, there is nothing else you can tensor it with. But maybe you are doing more like a mathematical thing than but concretely you will have some number of qubits and then there is nothing to tensor with.
Yes, I think I should go ahead and move on just to keep pace with the rest of the talk. But we can certainly discuss this issue about free states later. Okay. So now we have defined the resource theory of uncomplexity, and we want to move on to the operational task of the theory. So there are 2 operational tasks that we discuss in our paper. The first is uncomplexity extraction. So we want to start off with some arbitrary state and extract out uncomplex qubits. So qubits close to the all 0 state. And so the idea is that we start off with something relatively complex. We're trying to extract or distill out something uncomplex. So I don't know if any of you all are familiar with SpongeBob. There are a couple of elucidating parts of an episode that I remember long ago that kind of exemplify this, at least on the level of analogy. Starts off with something that's highly complex, and he's able to perform some allowed operation in order to produce something distilled uncomplex. Okay. The other operational task, which oddly enough has another analog within the same episode, is uncomplexity expenditure. So the idea here is that you start off with the resource you desire and you want to expend it in order to create some state that you want. So in this case, it starts off with the marble, which is the simple resource, is able to, by some operation, create some state. Here, the statue of David. Okay. So let's begin with uncomplexity extraction. So let's discuss the procedure and then we will talk about the task. So the procedure is relatively simple. As I said before, we start off with some state, we apply some allowed operation, and we want to extract the resource under question. So in this case, we have some n-qubit state rho. We apply our fuzzy gates, so that's our fuzzy operation. And then at the end, we select some W number of qubits from the n. And the idea here is that we want to have W qubits that are relatively close to the L0 state. So we perform the above, and we have some parameter delta greater than or equal to 0. And the task is to perform a set of fuzzy gates and to choose an appropriate subset of qubits W that will give us a state that is delta close and trace distance to the L0 state, 0 to the W. Okay. And importantly, it doesn't need to be exactly the state, but it just needs to be relatively close. So that's the purpose of the picture on the right, some approximation to the circle I mentioned before. So let's talk about uncomplexity expenditure. This is the other operation. Here we need to give a somewhat more complicated setting before we talk about the procedure. So the idea here is that we want to create, we start off with, we want to utilize some number of states initialized or qubits initialized in the 0 state, and we want to create a state which is close to some desired state rho. So how do we determine if we succeeded? Well, in our setting, we have a computationally limited referee who wants to distinguish between rho and the maximally mixed state. So the referee is able to do this with a measurement operator Q, which is in a set M sub R. And I'll define that in a moment. And the referee wants to guess rho with probability greater than or equal to eta, okay, where eta is some parameter between 0 and 1. As an agent, we assume that we know Q, and we hope to create a simulacrum of rho that we call rho tilde to fool the referee in this hypothesis test. So let me take a moment to define what M sub R is. So M sub R is a set of relatively simple measurements. So the idea is that the referee can do two things. First, the referee is able to apply some number of R gates, where R is greater than or equal to 0, and fuzzy gates, I should say, and thereafter able to perform some projective measurement, either just leaving a qubit alone or checking or projecting it onto the state 0. So basically checking to see if it is close enough to 0, or if the referee doesn't feel certain enough that he can verify that, just won't measure it at all. So the procedure here is as follows. You're an agent. You're able to borrow W uncomplex zeros from a so-called uncomplexity bank. So this is the number of zeros you think you can use in order to fool the referee. And so you're going to get an n-qubit state altogether. The rest of the state that you'll receive from the bank will just be some arbitrary n minus W qubit state. Just as you can see in the picture above, we can just call that junk, okay? So you start off there. The hope is that you need to use as little of the resource as possible in order to fool the referee. And so you start off with what you're given from the uncomplexity bank. You apply less than, or you apply at most R fuzzy gates, and then you get some state rho tilde. That's a simulacrum. Afterwards, you give it to the referee. The referee is just performing a hypothesis test between rho and the maximally mixed state. And the hope here, the task, is that the referee, upon receiving rho tilde, will guess that he's received rho with probability greater than or equal to eta. Okay, so once again, there is some allowed error in our task. Here, you don't have to exactly produce rho. You just have to have the referee guess that rho tilde is rho with some specified probability. Okay. So now let's talk about the complexity entropy. So there are a couple of motivations for the complexity entropy. First is that complexities, or that entropies are used to bound efficiencies of operational tasks. The perhaps most well-known example is the use of Shannon entropy to quantify the limits of data compression. And second of all is that we want to have an entropy that quantifies how uncertain a state looks by a computation limited observer. If we were to just allow our referee to have to use any measurement operator, then we would no longer be within the realm of complexity. I'll discuss this in a moment whenever we look at limiting cases. But yeah, the idea is that if I have a state that is very complex and I have computation restrictions, so I'm not able to apply a lot of gates as an observer or a referee, then whenever I do my measurements, most states look very close to the maximally mixed states. So in that sense, they have high entropy relative to my ability to probe them. Whereas if I were able to apply as many gates as I want and I had absolutely no uncertainty in my gates, so my fuzzy gates had a parameter of epsilon equals 0, then I would be able just to simply, in an idealized case, perform the exact unitary I want to get it back to the all-zero state. I could say, oh, it's a pure state. Any pure state has no uncertainty. It has an entropy of 0. So here we want to use an entropy that actually takes into account the computational limitations relevant to complexity. So now let's give the definition of the complexity entropy. So the complexity entropy of an n-qubit state rho for some parameter eta between 0 and 1 is given as follows. Okay. Let's talk about what each of the components in this formula means. It's important that we understand this entropy. So here we see that we're minimizing some quantity, looks like a surprisal, of some trace of a measurement operator Q. Now Q is sourced from this set I mentioned before, M sub R. So Q, it comes from a relatively simple measurement. We're allowed to apply at most R gates. And we have to ensure that our measurement Q successfully identifies rho with probability at least eta. Okay, so that's constraining the type 1 error. After that, this minimization, the purpose of it is to minimize the type 2 error. So that's the error that we would actually, that upon receiving let's say the maximum mixed state of the referee, that they would guess the state rho.
I have 2 questions.
Yes.
What is MR? Is that the EOBM, like minimization of MR?
Yes, yes. So, okay, is that clear?
Yeah, and then the second question is, are you missing rho in the trace of Q in the log?
No. So that's one of the interesting parts about this definition. So you can see there are a couple of constraints we have in our minimization. First, that Q is in that set M sub R, and then you see underneath that, we have that the trace of Q rho is greater than or equal to eta. So here, as long as Q is within the set of relatively simple measurements and it successfully identifies rho with high enough probability, it's fair game. Now we're just looking at these sets of measurement operators, and after that, we just want to minimize the type 2 error that we can get among the set.
So, so you're saying trace of Q still has some meaning of probability?
Yes, or at least it's very directly related to a probability. So in the next slide, I'm going to give some intuition. We're going to look at limiting cases. So perhaps this will clear up soon. Okay. And how do I do?
A quick question.
Yes.
Is the claim that this quantity that you define, is the claim that this keeps growing for exponential long amount of time?
No. The claim here is that this is an entropy which quantifies the efficiencies of the operational task I discussed before.
It's an entropy that quantifies the efficiency of an operational task.
Yes, there are a couple of theorems that I'll get to at the end of the talk that feature this complexity entropy.
Okay.
Yeah, so to give a bit of intuition for this complexity entropy, let's look at a couple of limiting cases. So the first is we can look at a low complexity state, so the all zero state, and so in this case, for some performable Q that's equal to, so you can see the two parts of the measurement operator, we have some unitary use of R, and then we have the, so that's the circuit we apply with complexity at most R, and then we can project onto the all zero state here. We're very close to the all zero state already. In this case, we'll find that if we look at the measurement operator, really what Q is doing is it's, or the trace of Q, it's counting the number of qubits that we can project onto the zero state. So if we feel quite confident that we're close to the zero state, then we'll still satisfy that bound. Trace of Q rho is greater than eta. Okay, and in the limiting case of this all zero low complexity state, we can project onto all of the zeros. Perhaps if we're actually in that state rho, we won't even have to apply unitary. We can just immediately project onto all the states. So in that case, Q more or less will be this projector onto the n qubits. And then we will see that the trace of Q will just be 1. So the log of 1 is just 0. So that checks out. The low complexity state has in the limiting case, it has 0 complexity entropy. In the high complexity case, we may only be able to satisfy that bound by say that we're not able to apply mini gates R. We won't be able to feel confident projecting onto any of these qubits, the zero projector. So in that case, we have to leave them alone even after we apply our unitaries. And so our Q, the best Q that we can do will just be the identity operator. And so, or I guess the n-fold identity operator, perhaps we can think about it that way. And each of those qubit identity operators will contribute a factor of 2 to that trace. We get 2 to the n, and then the logarithm of that is just equal to n. So in the limiting case, the high complexity state will give us a complexity entropy of n. And perhaps some of you are already familiar with this, but there's a very close relationship to the complexity entropy and what is known as the hypothesis testing entropy. So the hypothesis testing entropy quantifies the uncertainty that we get in a hypothesis test between a state rho and the maximally mixed state. So it's very similar to the setup that I discussed for uncomplexity expenditure. You have a referee doing a hypothesis test. They want to distinguish these two states. And so the hypothesis testing entropy. As you can see, I've boxed it down below in the green. It's very similar to the complexity entropy. In fact, the only significant difference is just that is that in the complexity entropy, we are only able to perform relatively simple measurements that have at most complexity R. Okay, whereas in the hypothesis testing entropy, we could apply any Q, any measurement operator. Okay, so hypothesis testing entropy is similar in the sense that it's like the complexity entropy, but it lacks the computational restrictions. So we need those computational restrictions in order to, basically not trivialize complexity. Okay.
Sorry, could you go back to the previous slide?
Yes.
So
the slide or the one before?
This one.
Okay.
So in this slide, we have H, eta, H, and overall. Looking at minimization of Q over here, right? So you're saying that this is a definition that used in hypothesis testing?
Yes.
Okay, so
Hypothesis testing entropy.
yeah, so okay, I see. Okay, so this one Q is obviously POV because it's bounded.
Exactly.
So previously, like MR that you had in the previous slide, actually Q is not necessarily POVM.
Yeah, it's a POVM. It's just a POVM of the form. So you see here how I've written the Q's and the arguments. That's basically, so, on the outside, you would have some unitaries with composed of at most R fuzzy gates. So that's the use of R on the outside. And then in the middle, you have some, some set of projectors. So each qubit, you're either choosing to project, have the zero projector or to have the identity operator. So the low and high complexity cases, we have, the extremes where it's all zero or all one, but you could, choose, okay, which W am I looking at to project onto the zero or just to leave alone.
Okay. So this is actually in analogy of hypothesis testing. This is one shot.
Yes.
Compared to like asymptotic.
Yes.
Okay, thank you.
Okay.
Can I also ask a question? So, again, in this high complexity state, the choice of Q, so high complexity state I can write as like some complex unitary acting on get zero. Right? So can't I just use the same Q as in the low complexity state? But instead of UR, I will use the unitary that was used to generate rho.
So the issue, I think I understand your question. If this doesn't answer your question, just follow up. So the idea is that we need some Q that will satisfy the bound of the type 1 error bound so that the measurement operator will identify rho with probability at least eta. And so in any case, we can always use the measurement operators of the high complexity case. We can always start off and just do nothing and then, apply, or we can always just, project onto none of the states, apply some unitary, and then we will get an entropy of at least n, because n is the maximal.
But eta will always be 1, right? If you use a complex unitary.
Sorry, I didn't hear that.
Because, I mean, if I use the complex unitary in the definition of Q, in the choice of Q, then eta will always be 1 because I'm just removing the unitary in the row by the unitary in Q. So I just left a trace of get zero brought through.
Yeah, so perhaps the confusion here is coming from the minimization part. So I can always use the projector of just the identity operator, but if it's possible for me to use a projector that has more zero projectors, like single qubit zero projectors, then that will minimize the, that will produce a lower kind of surprisal here in the definition. And so that will give a lower quantity, and here the entropy is defined as the minimum.
I see, okay.
Okay. Okay, so let me move through the last part of this relatively quickly, just so that I'm good on time. So the last part of this talk is the optimal task efficiencies. And we have a couple of theorems, one corresponding to uncomplexity extraction, another to uncomplexity expenditure. And each one establishes the existence of a protocol achieving the task and the near optimality of that protocol. So the first is the theorem for uncomplexity extraction. By the way, these are all very clearly given in the paper. So if you want to follow up on some of the details in the proofs in the appendix of the paper, that's where you'll find them. So here the idea, going with the protocol before, is that we have some n-qubit state rho, an R number of gates, and some parameter delta to quantify the success of our task. So if we assume that delta is at least R times epsilon, then okay, there's a little bit of a technical part. For a certain range of eta, we know that the protocol will, some protocol will extract n minus the complexity entropy number of qubits. Okay, so that's the existence of some protocol that can achieve that level of extraction. And then conversely, we know that every uncomplexity extraction protocol will be less than or equal to this quantity. So in that sense, we've established the near optimality up to this, you can see delta factor, okay. So let's look at a couple of limits, the low complexity limit. So in the low complexity limit, we see that some protocol will extract n qubits, okay, and all others will extract less than or equal to n qubits. So if you were to, we established previously the low and high complexity limits. So this all checks out. Basically, if we have a very uncomplex state, then we're able to extract a lot of uncomplexity. Okay, and in the high complexity limit, we see that the complexity entropy is equal to n. And so here in the statement of the optimal extraction protocol, W will just equal 0. In other words, the best we could do is extract 0 qubits. So all protocols extract 0 qubits. Okay, now let's talk about uncomplexity expenditure. So here again, we start off with an arbitrary n-qubit state rho. We have R and delta, and we assume that delta is at least 2 times R times epsilon. Now here we can choose any eta, and we say that for any junk state, sigma, so n minus W qubit state sigma, that rho can be successfully imitated with n minus the complexity entropy number of uncomplex zeros. Okay, so this is telling us how many zeros we need to get from the uncomplexity bank in order to simulate rho effectively. So again, we look at the low and high complexity limits. In the low complexity limit, rho can be imitated with n qubits. So in that case, we're just trying to imitate an arbitrary n qubit state. We start off with low complexity, and so we're going to need a lot of qubits in order to get there. In the high complexity limit, it's going to be the opposite. Okay, so the high complexity case, the referee can't do very well to begin with to distinguish the state rho and the maximally mixed state because of the complexity restrictions. So the referee isn't doing very well already. And so we can throw in just about anything and the referee is still going to not do much better at distinguishing the two. So that's why we don't need very much to get by in order to succeed in the imitation task. Okay, so that basically concludes the talk. Let's summarize what we did. First, we defined a resource theory of uncomplexity, after which we discussed operational tasks that can be performed within the resource theory. From there, we defined a complexity entropy, whose purpose is to quantify the optimal efficiencies with which we can perform the task. Okay, let me go ahead and skip over future research just in respect of time, but you can see there's some interesting connections thinking about complexity, entropy, black hole physics, and phases of uncomplexity extraction that can be considered when looking at the different parameters R, epsilon, and eta discussed before. Okay, thank you. This is the paper, Resource Theory of Quantum Uncomplexity, from which this work stemmed. Thank you.
Thank you so much. Are there any more questions for Anthony?
I have a question. So I have a question about complexity entropy.
Mm-hmm.
So could you remind me the physical interpretation of that entropy is, you said it's analogous to type 2 error in hypothesis testing.
Yes, let me go back to this slide. Is this the one you're thinking of?
Yeah, can we go back one slide?
Yes.
Yeah, this one, yeah. So yeah, so this minimum possible uncertainty. Yeah, so what do you mean by the last sentence? Like complexity entropy gives the minimum possible uncertainty due to the type 2 error. So it gives you the lower bound of the type 2 error. Is that what it is?
Yes, essentially. I'm not entirely in love with my phrasing there. I'm considering changing it. If you're familiar with the idea of surprisal, then you can think of up to a sign, the quantity that's being minimized as a surprisal. Okay. So, trace of Q will, with these relatively simple measurements I discussed, you're applying some unitary outside of these projectors that are either going to be 0 or 1. So really what trace of Q does is it just counts the number of 0 projectors or the number of 1 projectors that you have. And so if you put a minus sign and bring it inside, then you can, you're going to have the logarithm of some 1 over 2 to the some power. So it's very much like a surprisal, and in that sense, you're minimizing, or yes, you're minimizing that quantity, and that's really the type 2 error that you get.
This is really a one-shot entropy. It's just that he has trace of Q times identity because his distinguishability problem is with respect to identity, so he's dropping identity. That confused me for a while. But
yes, it's very similar.
It's just it's an exact parallel of what you do in hypothesis testing. One-shot hypothesis testing.
There is a quantity which surely you're familiar with, the hypothesis testing relative entropy. And so you get something very similar if you look at the hypothesis testing relative entropy, and then you just the hypothesis test that you're making is between the some state rho and the maximally mixed state.
Yeah, but this is a one-shot version. This is the only difference is that this is one shot.
Okay. So yeah, I was about to ask about relative entropy part, because in hypothesis testing for this asymmetric hypothesis testing, meaning that you put the bound on type 1 error, you think of the optimal measure for type 2 error. Now, in hypothesis testing, you have relative entropy, like Hertz divergence or whatever, what appears. Here, like you have like entropy. Have you thought of any like complex relative entropy thing?
Yes. In fact, as I was working through a problem, and as I established and proved the second theorem about uncomplexity expenditure, and I initially began, working with the like a complexity relative entropy in that hypothesis test, and it just so turns out that if you decide to define the hypothesis test such that the referee has minimal knowledge of your state. And so you choose, in a general hypothesis test, you can have two states, let's say rho and sigma. And if you make that sigma just equal to the maximally mixed state, assuming maximal ignorance of the referee, then it reduces to this form. And so here the complexity entropy, can be defined like so, but I really do think it is useful to think in terms of the a complexity relative entropy in order to understand kind of implicitly there is some hypothesis testing notion going on here.
Infinite Renyi relative entropy. That's literally what it is. Sandwich Renyi. Take the limit of n going to infinity. This is what you should get, right? The thing is that's a one-shot.
And also relative entropy between density matrix, arbitrary density matrix and identity. So it becomes entropy. Oh, okay, I see. Okay, good. I see. Thank you.
Yeah.
Sorry, I have one last question.
Okay.
I missed when you say high complexity limit, like what kind of limit you're taking?
Are you talking about this slide or are you talking about later in the?
Any like in general, right? What do you mean by high complexity limit? I think I missed.
So in the case, I guess maybe a more precise way to think about it is like the limiting cases of measurement operators you would need to, for certain either high or low complexity states. So the idea is that if I have a state that's very low in complexity, like the alt-0 state, then I don't need to do very much in order to get it delta close to the alt-0 state. Perhaps I may have to do nothing at all, right? So in that case, I'm able to project onto, if you look at this, this type 1 error bound, that the trace of Q is, trace of Q rho is at least eta. Well, if Q, in the very best case scenario, I could just, if rho is pure, I could, if I didn't have any restrictions on Q, I could just choose Q to be the projector onto rho. I could just make Q equal to rho. But here we are only able to perform these relatively simple measurements. And so in general, I can't do that. But if rho is really, really close to the alt-0 state, then I can choose a Q whose projector is the alt-0 state. And I'm still going to, Q will still identify rho with high probability. In the limiting case where rho is exactly equal to the alt-0 state, I could just choose Q to be the alt-0 projector. And I'm going to get, that probability is going to be equal to 1, and therefore it is certainly going to be greater than eta, which is bounded between 0 and 1.
Okay. Thank you.
Mm-hmm.
Any last questions for Anthony? Here or online? I don't know if people are still online. If not, let's thank Anthony again for the wonderful talk.
Thank you.
Thank you so much. So we'll post a video on YouTube. We'll send the link to you.
Much appreciated. Thank you again for letting me join you. And if you have any questions,